to be IP rated. So let's check that now. It's a good job I'm doing this, Tone.
Harsh.
You can reach the floor, can you, I take?
It's down on the floor.
Lovely. So that's 2.4 metres, so this is a tick.
Next we have suitability of equipment for installation in a particular zone. For example, switchgear and control gear. Well, here the light switch and the fan isolator are actually out of the room, so this is not applicable.
Our final box for this location is suitability of current using equipment for a particular position within the location. So here we're checking the requirements of regulation 701.55 are complied with and includes equipment such as electric showers and any luminaires. So for this installation, it will be a not applicable.
The final box on the schedule provides the option to expand the form for other special installations or locations. It doesn't apply to this site, but it could include saunas, swimming pools and jacuzzis.
For those, we'd have had to go to Tony's house to do the report.
Only my country house, Dave.
The UK one?
Yes, well, yes. I've verified the CPCs exist for accessories. I now want to verify the continuity of the main protected bonding conductors. Again, I'll be using the R2 test method.
To do this, Tony will leave the conductors disconnected at the MET and connect the R2 wand lead, which has been nulled out on the test instrument. So first to the water.
Right, well here we are at the water, and we're going to test for the main equipotential bond to the water. And here we are, I've actually got a reading of 0. Now, what we've got to consider, of course, is this acceptable?
What Tony is referring to here is that it's vital not just to accept readings at face value, even if they are lower than any value required to comply with the regulations. When measuring the resistance of a conductor, you can use tables in the on-site guide to calculate a comparison value. For example, a 10mm squared copper conductor has a resistance of 1.83 milliohms per metre.
Well, is this reading of 0 realistic? Well, if that wall wasn't there, I could more likely touch the consumer unit. So the length of the cable is only about 2 to 3 metres. Now, if you consider the resistance of 10mm cable of 1.83 milliohms per metre, it's very, very small. And I would imagine the resolution of this instrument can't measure that low. So 0 would have to be okay for this. I will now go and repeat this for the gas, and the procedure will be exactly the same.
Our next dead test is to verify the continuity of ring final circuit conductors. Although we verified that the CPCs are present as part of the R2 tests and visual inspection, it's vital with ring circuits to make sure that the CPCs, lines and neutrals are actually connected into a ring. If not, this circuit will not be able to carry the full load expected of a ring circuit. Tony has also left the main protective bonding conductors disconnected to help eliminate any parallel earth paths through metallic pipework and the like.
Now I've disconnected both legs of the ring, as you can see. I'm going to carry out my end-to-end test. I have nailed out the instrument. The first thing I'm going to do is on line to line. Now I have a reading, so that proves it is a ring, and the reading I've got is 0.72 of an ohm. Now I'm going to do the same with the neutral. Once again I've got a reading, so it's a ring, and I would expect roughly the same, and believe it or not, it's exactly the same, 0.72 of an ohm.
Well, sometimes there are small variations, which can be caused by bends in the cable, causing one conductor to be slightly longer than the other. And of course, the tightness of each and every termination will also have an effect on the overall resistance reading. Finally, Tony will move on to measuring between each of the CPCs. Now, with twin and earth cable, it's important to remember that the CPC, in many cases, will have a smaller cross-sectional area than the live conductors. The most commonly used twin and earth for a ring circuit has 2.5mm squared live conductors and a 1.5mm squared CPC. And proportionally, this is about 1.67 times smaller than the live conductors, so should have a resistance 1.67 times higher.
Now, as Dave said, 1.67 times the line conductors. Now my line conductors were 0.72 of an ohm, so I'm looking for a reading in the region of about 1.2 ohms. So let's see what we get. Well, I've got a ring, that's for sure, and I've actually got 1.17 ohms, so that's perfect. Now I'm going to repeat this for all the other circuits.
With initial verification, it would be necessary to carry out the crossover test on each ring, which includes going to socket outlets and taking additional readings. So why isn't this necessary for periodic inspection and testing, Tony?
Well, we've got to remember that this is an installation which has power. So I can use my earth fault loop impedance test later on, not only to get a value of ZS, but also to confirm polarity.
And we'll see this very shortly. The next dead test Tony will undertake will be an R1 plus R2 test at the furthest point of any radial circuit, for example, the lighting circuits. R1 plus R2 will give us a value which, if added to the earth fault loop impedance external to the installation, ZE, will give us our earth fault loop impedance for these circuits. Now doing this test means that Tony will not have to work on live exposed electrical conductors, so reducing the chance of receiving an electric shock. This then complies with the Electricity at Work Regulations 1989, which only allows work on or near live conductors if there is no other way of obtaining the results.
At the consumer unit, I cross-connected the line and CPC, as you can see. Right, so I'm going to connect between the CPC and the line. And as you can see, I've got a reading of 0.3 of an ohm. And this I'm going to record as my R1 plus R2. Now, if I've got a high reading here, this more likely would be because I'm coming through the resistance of the lamp, and this would indicate to me that I've got reverse polarity.
This means that there will always be a live pin at the light pendant, meaning the users are at risk. It would have to be classified as a code C1 on the report. So we've shown that the R1 plus R2 will also prove polarity for a lighting circuit without the need to remove lamps.
Just a quick word about polarity. If there had not been an electrical installation certificate for this installation, I would have undertaken this test at every switch position to verify the polarity.
Later on in the video, we'll see how to determine the earth fault loop impedance of these circuits and how to check that this is acceptable. Okay, we've finished the visual inspection of a sample of electrical equipment around the property. We've also undertaken R2 tests and R1 plus R2 tests where appropriate, and we've kept our sketch updated, including any observation codes, R2 readings and the R1 plus R2 readings of lighting circuits. So what now, Tone?
What I would like to do now is undertake an electrical test to verify that this property does actually have an earth, rather than just assuming so because we've seen a cable. But first, I want to check the polarity on the incoming supply. What I'm going to do here, I've got my voltage checker. I'm going to actually check the incoming supply first. Remember, always go on the neutral first. And you see there, we've actually got a live. Now what I'm going to do is check polarity. So I'll actually go onto the earth. I'll go onto the neutral. As you can see, we've got nothing there. So if I go onto the line, there we can see that we actually got correct polarity for this installation.
So the polarity test is correct. So let's now move on to our test which will verify ZE, the impedance of earth external to the installation.
What I'm actually going to do is to verify the prospective fault current for the installation, which is the highest impedance reading of two tests. For the first, which is prospective earth fault current, as you can see, I've disconnected the earthing terminal from the MET. Now this instrument only needs 2 leads for this test, so I'm connecting first to the disconnected earth conductor and then to the incoming line. So first to the disconnected earth conductor and then to the incoming line. And the reading I've got is 0.17 ohms with a PFC of 1.37 Ka.
The distribution network operators declare the value of impedance for a TNCS supply to be 0.35 of an ohm. So our 0.17 is lower than this, most likely accounted for due to being close to the local supply transformer. But don't forget that where network switching takes place, this can also cause impedance values to go up or down.
Now I've reconnected the earthing conductor and will now undertake the reading of the respective short circuit current. This is taken between line and neutral on the incoming side of the main switch. Now the reading I've got here is 0.16 ohms and 1.41 kA.
A quick word about the reading of fault current. It's important to realise that this is actually a calculation based on the nominal voltage, in this case 230 volts, divided by the impedance reading. It's not based on the actual voltage at the time of test, and it's not measuring current. To do that would take a much larger instrument, certainly something that Tony couldn't tuck under his arm. Mind you, it could be handy for him to stand on it sometimes.
Harsh. So I've now confirmed that we have an earth. We have a value of ZE and also the value of prospective fault current. In this case, it was prospective short circuit current between line and neutral which was higher and will be noted as our PFC. However, I wouldn't have been surprised if they've actually been about the same, because behind here is the pen conductor and I've only got about a metre of tails here, so there's only a difference between 25mm and 16mm for a metre, so they could well have been the same.
If the installation being inspected is a TT installation with an earth electrode, it is acceptable to use the PEFC method to provide a value for the resistance of the earth electrode RA, rather than undertaking the fall of potential method using test rods or similar tests. Our next test is the final dead test before replacing the cover and switching the installation back on. And this is to check the insulation resistance of the installation.
I'm going to undertake the alternative test method, which checks between line and neutral cross-connected together and the earthing arrangement. Remember that the earthing arrangement is the whole thing. So that's the MET with all CPCs and main protective bonding installed and the earthing conductor connected to the means of earthing, in this case in the meter cupboard. So that's why I'm undertaking this test after we have verified by both inspection and test that we have an earth.
Testing with line and neutral cross-connected means that equipment such as lamps will not interfere with the resistance readings. And electronic devices will also not be damaged, so they can be left in the circuit. Light switches must be in the on position, as are all circuit breakers and RCDs.
Now this is actually proved to be a bit of a bugger here because it's a split load board. So to join line and neutral together, I'll join the two lines together there, the two neutrals together there, and the line to neutral there.
The required test voltage can be found in table 6.1 of the regs. In this case, it's 500 volts. Although the test instrument has a current limiter, so you can't receive a serious electric shock, it's still quite an unpleasant experience if you come into contact with the test voltage. So it's good practice, therefore, to warn any other person in the building, because if there is an insulation fault, this 500 volts could be present on conductive parts such as a radiator or appliance casing.
Although 500 volts is the required test voltage, it's good practice to test first at 250 volts because this will not damage your electrical equipment if there's a problem. Right then, as you can see, I'm on the line and neutral connected together. So let's go on to the earth. Let's do our test. And as you can see, we got a reading of 7.5 megohms. Well, I'm happy with that reading, so I will now test at 500 volts. Press the test button. And I have a reading of 7.53 megohms, which is more than acceptable.
The minimum acceptable insulation resistance for a circuit in the regs is 1 megohm. But an experienced inspector will need to consider very seriously whether readings approaching this level in an installation would be satisfactory. Consideration should be given to the age of the installation and previous test documentation, if any is available. If a low level of resistance was accepted, I would expect the inspector to reduce the time period for when the next EICR is due, because obviously the insulation is degrading.
Now, although I said 7.53 megohms is acceptable, and clearly it is because it's more than 1 megohm, for an installation this age, I must admit, I would have expected to be a bit higher. So I think what I'll do when I get back to the office, I'll actually consider that I won't be putting 10 years to the next inspection.
A low reading, which is however a pass, could be a C3, unless the inspector feels that remedial action is required, in which case a C2 will be given. C2 is also the code to use if the reading is below the 1 megohm required by the regs.
I can now remove my cross connections, reinstate the lid and switch the installation back on. To determine the value of ZS for each socket outlet circuit is very easy. All I have to do is to go around to each socket in turn, plug the 3-pin lead in, and whatever the highest reading for that circuit, that will be the reading which I will record. As you can see, I've got a reading for this socket of 0.26 ohms. I will now go and repeat it on all the other sockets.
ZS is used to determine whether a protective device will operate within the required time when there's a fault between line and earth. For a final circuit on a single-phase TN installation, this is 0.4 of a second. Maximum values of earth fault loop impedance for different types and rating of protective device are given in tables 4.1.2 to 4.1.5. So for our lighting circuits, we can determine ZS by adding ZE, which we determined during the prospective earth fault current test, to our value of R1 plus R2. Now looking at table 4.1.3, we can see that the maximum ZS for the 6 amp type B circuit breaker to operate is 7.67 ohms. Now our ZS is well below this, but it's important to remember that the regulations do require an adjustment to the figure to allow for the increase of the resistance of conductors with increase of temperature when a circuit is under load.
You can find guidance on this in Appendix 14, but I always call it the 80% rule of thumb method. So basically the tabulated ZS needs to be reduced to 80% of its value. You can do this just by multiplying by 0.8. This is then compared to the measured ZS. This check needs to be undertaken for each circuit. But where a non-time delayed RCD is used to provide either additional protection, such as you have here for the socket outlets, or for full protection, then the maximum values of ZS in table 4.1.5 may be applied instead of those in the other tables.
As this installation has an RCD, we now need to check that its operation complies with the regs.
For the first test, the RCD should operate at the rated current within 200 milliseconds. As you can see, I've got this side set on ×1. This side is set on 30 milliamps, which is the rating of the device. Now if I press the test button, and as you can see, we've got a reading of 18.3 milliseconds. Now what will happen, Dave will reset the RCD and we'll do it for the other side of the waveform. Now, if you look there, you can see I've changed the other side of the waveform. So let's repeat the test. And we've got 26.1 milliseconds. And as that's the highest reading, that will be the reading that I will record. For the second test, we select 5 times the rated current. And here, an RCD provided for additional protection against electric shock must operate within 40 milliseconds. So I'm going to change it to 5 times. Press the test button. And then you can see I've got a reading of 15.6 milliseconds. Now I'm going to change the waveform. Press the test button. And I've got a reading of 30.5 milliseconds. And that will be the reading that I will record.
Finally, for RCDs, it's important to check that the manual test button on the device also causes it to operate. All done, TC?
I think so, yes.
Good result. We've now completed our EICR, so we'll do a quick check through the form to make sure we haven't missed anything, and then head back to the office. Back in the office, Tony has compiled the report, so let's look at a few pertinent points.
Well, looking at the front page, I filled in the extent of the electrical installation. I've also filled in the agreed limitations and the operational limitations. I've put down the reasons for this and whom they were agreed with.
Our purpose of report was mortgage application because the house is going onto the market. It would not be right to put something like client request or to check safety here, although if you put to check the safety of the electrical installation after flooding, this would be acceptable.
For the summary of the condition of the installation, I've written this. The installation is in a generally good condition, with adequate earthing and bonding arrangements. The electrical equipment, wiring and accessories inspected are suitable for the locations installed. The consumer unit is correctly labelled, but only provides additional protection against electric shock by RCD to the socket outlet circuits. The installation resistance was lower than expected, so may indicate some deterioration of the basic insulation. I've also drawn a line through unsatisfactory, which indicates that the installation is in a satisfactory condition and safe for continued use.
This ties in with the observations part of the NICEIC form, which lists the C1, C2 and C3 observations. The Electrical Safety Council's Best Practice Guide on Electrical Installation Condition Reports provides a list of correct terminology to help fill in this section. We've only got C3s on here, which is why we're happy to declare that this installation is satisfactory. But don't forget, just a single C1 or C2 would have resulted in unsatisfactory.
With regards to the supply characteristics and earthing arrangements, this was fairly straightforward for our installation. But don't forget, for a property with backup or alternative supplies, it will be necessary to provide the supply parameters information for these as well.
We've also got a box to write down the date of the next inspection. So what are you going to put down, Tone?
Well, like I said on site, although the insulation resistance values pass those required by the regs, they aren't as good as I would like to see for a property of this age. So after due consideration, I'm going to reduce the period to the next inspection to 5 years rather than 10.
And are you going to put a date if there are C1s or C2s?
Oh yes, Dave. Let me read you exactly what it says in this section. Provided that any item at F, which has been attributed a classification code C1, which is danger present, are remedied immediately, and any items which have been attributed a code C2, potentially dangerous, or require further investigation are remedied or investigated respectively as a matter of urgency. Items which have been attributed a classification code C3 should be improved as soon as practicable.
So that paragraph makes it very clear that this is a report from us, the contractor, to the homeowner, but the responsibility for remedial work clearly lies with the homeowner.
Yes, Dave, but I should point out that the contractor carrying out the report also has a responsibility to point these out to the homeowner and perhaps discuss it with them. You just don't give it to them and that's it.
Our EICR is now ready to be put together in a professional binder with the sketch and the guidance for recipients information, which will help the client understand the information contained, especially on any codes given to defects. This would also include photos of defects, especially those awarded a C1 or C2.
Although the report itself is not a list of remedial work, it's a good idea to include with your report an additional letter listing the work and perhaps even giving an estimate for it, which may result in you obviously getting the work.
Well, there we are. We've given you a solid introduction to undertaking periodic inspection and testing using a domestic electrical installation condition report.
We've shown you a methodical approach that you may like to use. But don't forget that not all electrical installations are the same, so use your knowledge and experience to adapt the approach as required.
And don't forget that there's a wealth of information on the topic of inspection and testing and how to fill out documentation. Not just the videos featuring Tony and myself, but also resources such as the Best Practice Guide from the Electrical Safety Council. It's all good stuff and well worth keeping in your toolbox.
So you've got a big toolbox then?
It's not bad, DC, almost as big as your wallet.
Oh dear, thank you.
See you
See
soon.
you soon.